Hey there. So welcome to the third and final and most elegant way to do this integral right here, which is using some clever observations and a matrix. Two matrices actually. So let's get started. So if you look at the graph of this function, it looks something like this, and you may be wondering how I came up with this graph, because like this function doesn't even seem evaluatable, but it is actually, because if you notice that if you call this entire thing y, then this is also y, because they are the same thing essentially. But from here you can make an equation involving y and x, which will basically give you a function y in x. So you'll have the equation y equals a sine of y plus x, because you have sine of y plus x, right? So you have this equation, you can plug it into a graphing calculator and you'll get a graph which looks something like this. Maybe I've like exaggerated its skew a bit, but it looks something like this. You can plug it into some graphing calculator of your choice and see. So where did I come up with this pi by 2 minus 1? Well, this is not from the graph. This I actually derived in a previous video, the first video in this series. So if you haven't watched it, go and check that out, and also check out the second video. And well, that's where I came up with this. And it's obvious, right? The max value of y is obviously 1. It can't be more than 1 because y is equal to sine of something. So sine of something can't be greater than 1 because we are in the real domain right now. And you can just set y equals 1. So you'll have 1 equals sine of x plus 1. So you can solve that x must equal pi by 2 minus 1 in our particular interval from 0 to pi. There is no other value of x which satisfies this condition in this interval. So with that out of the way, what observations are we going to make? So we are on the first step right now, observe the graph. So if you like, maybe I should draw one more graph beside this to make the observation a bit more obvious, and that is the graph of y equals sine x from 0 to pi. It looks something like this, right? And this is of course 1 and this is pi by 2. So it's perfectly symmetrical. But what if I kind of like kept my hand above the y equals sine x graph and kind of pulled it over here and skewed it? In particular, I'm talking about applying a shear matrix to this graph. What if I did that to this graph? Would it look something like this? And if yes, what would happen to the area under the graph? I mean, after all, the integral is just the area under the graph, right? So if we can somehow figure out how to go from this y equals sine x graph to this graph, and we figure out what happens to the area under the graph in that process, then we've got our answer, right? Because the integral from 0 to pi of sine x is child's play. So let's try to figure out why it looks the way it does. So we are on the second step. So this graph is of course y equals sine of x plus y with x running from 0 to pi, right? That's what defines the graph. So what if I solve for x from here? So if you take the sine inverse on both sides, then you'll get sine inverse of y is equal to, the sine and sine inverse cancel out, x plus y. But in fact they don't exactly cancel out, because here you have x, like x can be anything from 0 to pi, but from here you'll get that x can only be something between 0 and pi by 2 minus 1. Basically what I'm saying is x plus y can be anything from 0 to pi in our case, but sine inverse of y can only be something from minus pi by 2 to pi by 2. So we have to extend the domain, the range of the sine inverse function somehow to fit our case. So how can we do that? Well, let's just look, let's just restrict ourselves till here, till x equals pi by 2 minus 1. Let's ignore this part of the graph. So in that case, x plus y will only vary from 0 to pi by 2, because if x is pi by 2 minus 1, we already saw that y equals 1 when x is pi by 2 minus 1. So that means that x plus y is pi by 2. So till there we are all fine. The sine inverse works just fine. So here we can say x is an element from 0 to pi by 2 minus 1. So that equation is fine for that interval, but what about the later interval? Well, here we have x plus y being between pi by 2 minus 1 and pi. So if I gave you an angle like 3 pi by 4, let's say, which lies between pi by 2 and pi, then, and I tell you that what is the sine, like I ask you what is the sine of this, so you'll tell me 1 by root 2. And then what I ask you what is the sine inverse of 1 by root 2, you'll tell me pi by 4. And basically what I'm getting at here is that we can extend the range of the sine inverse function by subtracting it from pi. So for this remaining interval, what we can do is we can say pi minus sine inverse of y is equal to x plus y, for x being between between pi by 2 minus 1 and pi. And this is justified because the sine of an angle is equal to the sine of pi minus that angle. So basically, if I have the sine graph y equals sine x, and I tell you to make this a function from y to x instead of a function from x to y, then what you can do is for x being an element from 0 to pi by 2. Now again, this won't be a function, it will be a relation, but that's just technical terms. So for x running from 0 to pi, you can just say x equals sine inverse of y. And for x running from pi by 2 to pi, you can say x is equal to pi minus the sine inverse of y. And that can do the trick. So here what I'm writing here as x is x plus y over here, because you have a sine function over here, you have a sine function over here. So with that out of the way, we have this, which is important. So how can we use this? Now if you we already saw that this graph looks a bit like you're skewing or shearing the y equals sine graph. So let's see if our hypothesis, you can call it, is actually true. So the best way to check our hypothesis is to find what matrix takes the y equals sine graph to this graph. So here we can solve for x. So maybe you can just take a shortcut and do this, add minus y to both sides, and you'll have solved for x. So now we have solved for x, and let's look at if we write this as a vector, then the vector will look something like this. The y coordinate is just y, but the x coordinate is sine inverse of y minus y, right? And we are asking what matrix when applied, what matrix should we apply to the y equals sine graph, which is basically the sine inverse of y and y graph, vector. So I don't have enough space here, maybe I should. So the question we are asking is what matrix, let's call it matrix A with the components as A, B, C, D. When I multiply it with the vector sine inverse of y and y, will it give me the vector sine inverse of y minus y and y? So what matrix A when multiplied with this vector will give this vector? And where do these vectors come from? Well, this is the x component, this is the y component, this is the x component, this is the y component, and here we have x equals this thing, and here x is equal to that thing. The y component is just y. So we are asking this question, and it's pretty simple to solve for A, B, C, D. Let's do that. So for case 1, maybe I should get rid of this stuff. So for case 1, we have when x is an element from 0 to pi by 2 minus 1. So we can multiply out these vectors, this matrix and this vector, right? Because we know that we know how to multiply a matrix and a vector. So what is this product? Well, it's a sine inverse of y plus by, and for the y component it will be c sine inverse of y plus dy, and we want that vector to equal the vector sine inverse of y minus y and y. Okay, fair enough. And obviously you can already see that there's an infinite number of solutions for a, b, c and d if you allow them to be functions of y, but we don't want all of that stuff, so we'll just keep them constants. So what constant should I keep a as a and b so that I get this in the x component? Well, a should be equal to 1 and b should be equal to minus 1, just simply equating the coefficients. So we have our matrix A. So A we figured out to be 1 and B is equal to minus 1. So let's put that in, and what C will be 0 and D will be 1. Again, for the same reasons. So A1, you can call it, for A in case 1 is this matrix. But why did we even figure this out? Like, now what? So we wanted to see what it does to the areas. So now I'll define the following space or this following area. Take the y equals sine x graph from 0 to pi, and we know that it at pi by 2 it touches 1. So take this area. So my area is defined to be the area between the y equals sine x curve, so let's call it C1, the first curve, y equals sine x curve from 0 to pi by 2, and it is also defined by this line and this line, right? So we can, instead of just calling them lines, we can make them into vectors. So the position vectors, so keep in mind I'm talking about the position vectors. Their tail must be at the origin. You can't just keep them over here. They always have to be at the origin. So the vectors will be this vector and this vector, right? But the problem is that this vector is not tail, it doesn't have its tail at the origin. So we can define this vector as so basically you can do this. So you want to define this vector right here, so maybe I should draw it in black to highlight it. You want to find this vector. Well, if you call this vector, I don't know, well, what letters can we use? P vector and Q vector. We know that Q vector plus our mystery vector, so let's just draw a black dot, is equal to P vector, right? Because of the triangle law. You take the head of this vector, keep the tail of this vector at it, and then draw the vector connecting the two, the tail of this and the head of that. So we have this equation. So our mystery vector, our black dot vector, we should fill it in to distinguish it from 0, is equal to P vector minus Q vector. So we'll define it that way, and we know that P vector and Q vector are both have their tails at the origin, so they are both position vectors. So we have turned our mystery vector into a relation between two position vectors. So what do we do with that information? Well, what is P vector? If you look carefully, P vector is right here. So that diagram is getting a bit messy, so maybe I should draw it here. So this is P vector with its tip at pi by 2, 1, right? So P vector is equal to the vector pi by 2 and 1. And what is Q vector? Well, it has its tip at pi by 2, 0. So that is equal to pi by 2 and 0. And of course we have the y equals sine x graph. And we already know that once we apply this matrix to the y equals sine x graph, it's going to transform into this curve right here, and the interval from 0 to pi by 2 of that curve is going to be this curve from 0 to pi by 2 minus 1. And to see where that, like, to get the you can say formalities, or I always forget the word, the rigorous part, yeah, the rigorous part of this argument, you can check out the first video. I've gone into rigor quite a lot in that. So if you want the rigorous part, you can go there, but it's pretty clear intuitively as well, right, that this part will, after applying the matrix, become this part, right? So we know that our area, this area, became like it was enclosed by this vector and this vector, and now it's, and this curve obviously. Now the curve has become this. Now we need to figure out what these two vectors become. So let's do that. So what does this vector become? The vector 0, or sorry, pi by 2, 0. Because we also have that vector as part of our boundary, right? So we need to see what happens to this vector and this vector. So the vector pi by 2 comma 0 just stays the same, right? Because if you apply this matrix to it, you can do it in your head. Multiply a1 with this vector, you will just get pi by 2 comma 0. So this vector stays as it is. So this is still our, sorry, it was q vector, right? So q vector stays as it is, goes till here, till pi by 2. And what about the other vector, the second vector, which is this vector right here, from 0 to pi by 2 comma 1? Well, we know intuitively that it must go here, and to see the rigor part, again go to the first video. So we know intuitively that it must become this vector. And what is this vector? Well, its tip is at pi by 2, minus 1 and 1. So we know that that this boundary part actually becomes something like this, right? So our new area looks something like this. So if I draw it again over here, so this sine y equals sine graph, sine x graph, after we apply this matrix, became this, and now we are talking about this part of the area. Well, it looks something like this. So if I draw the y equals sine of x plus y graph again, it looks something like this, with pi by 2 minus 1 over here, and our area in question, the area which I've colored in black over here, becomes this area. So maybe I should do it in red this time. It becomes this area, and what is this point? This point is pi by 2 comma 0, of course. So it becomes this area. And what is that area in terms of the integral? It's the integral from 0 to pi by 2 minus 1 of this function plus this extra triangle, right? So maybe I should get rid of this stuff, because okay, so I've rubbed most of the stuff other than the important stuff. So the area in question was the total area which I've shaded, and we know that the integral from 0 to 0 to pi by 2 minus 1 of y dx. Now what is y? Y is this function right here. So this is precisely equal to the red shaded area, right? And the black shaded area is just simply a triangle, which we can easily figure out. So what is the area of the triangle? Well, the base is 1, because this length must be 1, and the height is also 1. So the area must be 1 times half, which is half. So that area is half. So we know that the area which we are looking at is this plus half, right? And what is this integral? Well, that integral is the integral from 0 to pi by 2 minus 1 of y dx plus the integral from pi by 2 minus 1 to pi of y dx. So basically I've split it up about pi by 2 minus 1, which is completely legal. So we know that the area which we just found out is this area right here, the integral from 0 to pi by 2 minus 1 of y dx plus a half. So maybe we can add and subtract a half over here. So I'll subtract half here and add half here. So we know what this evaluates to, but we still haven't found it out, right? Because we know that the y equals sin x graph after transformation, and which transformation, specifically this transformation, gives you this graph. But how does that change areas? Well, that question is precisely answered by the determinant. So if we figure out the determinant of a1 specifically, and we multiply it by the integral from 0 to pi by 2 of sin x dx, then that will be equal to the shaded area. And what is the shaded area? It's this egg right here which I've drawn. So it's half plus the integral from 0 to pi by 2 minus 1 of y dx, right? So we have this equation, and well, what is the determinant of a? That's pretty simple to figure out. Well, determinant of a1, why am I calling it a again and again? Well, it's 1 times 1 minus 0 times minus 1. And what is 0 times minus 1? It's just 0. So the determinant is 1. So we have 1 times the integral from 0 to pi by 2 of y, not y, so this is sin x dx is equal to the integral from 0 to pi by 2 minus 1 of y dx plus a half. And well, what is this? We know that this is 1. You can evaluate the integral yourself. So this integral is 1, the LHS is 1, and the RHS is this plus a half. So we can subtract a half from both sides and this becomes half. And we have that this thing right here is equal to a half. So we have the first part of our answer figured out. And now you basically get the idea, right? Now what we did with the, so I have the y equals sin x graph here. Maybe I should draw it a bit bigger. So we figured out what happens to this half of the area. Now we need to figure out what happens to this half of the area. And we already know by intuition that that half must correspond to this remaining area right here, right? Because we know that it is bounded by this vector right here, and it's bounded by this vector right here, and it's bounded by this curve, right? And we already know that this curve transforms into this part of the curve after the matrix application, and it's not going to be this matrix specifically, it's going to be a bit different. So let's call it A2, and let's bring back our ambiguous variables a, b, c, d. So it's some matrix, we don't know yet, we'll find out. So after you apply this matrix a, b, c, d to this part of the curve, you'll get this curve, right? You know it pretty well by intuition, and if you want the rigorous part, once again go back to the first video. And we know that this vector becomes this vector, right? Because we already showed that. So I'm talking about this vector right here. It becomes this vector, right? So we have these two boundaries figured out, and just like previously, this vector will remain the same after transformation. So we'll figure out this matrix and then we'll get our answer. So okay, so we already figured out this thing right here, that this equation holds for the graph that we were looking at, for x being an element from pi by 2 minus 1 to pi, which is precisely the interval we are on now. So we have this equation. So x is equal to pi minus sine inverse of y minus y. And well, once again we'll do the same thing. We'll turn it into a vector. Well, what is the x component? It's pi minus the sine inverse of y minus y, and the y component is just y, and that equals to some matrix A2 with elements a, b, c, d times the vector. And now we won't have sine inverse of y and y, we'll have pi minus the sine inverse of y and y. So once again, if you haven't understood why this is the case, you need to go back till to where we discussed this thing, and you need to see what we did over there. So now let's get to figuring this matrix out. So once again we'll have the same equation. So once again we'll have the matrix. Well, A must be 1 and B must be minus 1 and C must be 0 and D must be 1. So in fact we get the same matrix all over again, and A2 is equal to A1, but that doesn't matter right now. It will matter in a future video maybe, because I'm going to make a video about this special case where, sorry, the general case where sine of x plus ny is equal to y, and how the graph of that looks and why does it look that way. So once again, back to the topic, we have this matrix right here, and once again we need to figure out what happens to the boundary once we apply this matrix to the y equals sine graph. So if you look at the y equals sine graph, it will look something like this, and this is the area in question, the area bounded by this vector, and this curve. And in fact we don't have to make it this vector, we can actually extend it and root it at the origin. That's completely fine, because that doesn't change the area, right? And if you are looking at all of those three together, you are basically looking at this area. Once again, we know that this area will, like, we know intuitively that this area must become this area right here. And well, what do I mean by this area? Well, this point is pi by 2 comma 0, this point is pi by 2 minus 1 comma 1, and this is just pi. So we know intuitively that it must become this area, and we want to figure out that what does this matrix do to that area. We know that intuitively this area should transform into this area in particular. So this point is pi by 2 and it should transform into this area, right? We know that intuitively. So we need to figure out by what factor does it scale that area, and we already know that this vector will remain as it is, because if you take any vector which is of the form x 0, then it will not be affected by this matrix, which is quite obvious because it doesn't scale I hat at all. So if a vector is a pure multiple, pure scalar multiple of I hat, then this matrix doesn't do anything to it. So this vector right here, which is a pure scalar multiple of I hat, must remain as it is. This curve becomes this curve, and this thing, this vector right here, we already know that it becomes this vector. So we know that the area in question is actually the second half of the y equals sine x graph, but after applying this matrix. So once again we can do the same trick. We can find the determinant, see what factor it scales this area by, and then we can find this area. So we already know that the determinant is 1, and this area right here is the integral of sine x dx with respect, sine x dx from pi by 2 to pi, and well, once again this is also equal to 1. So since the determinant of this is 1, it doesn't scale the area at all, so this area must be 1, and we already know that this area is half, and this triangle right here has a base of 1 and a height of 1, so this area is half and this area is half, so half plus 1, 2. So this integral is in fact 2, and I hope you guys like that. Thanks for watching.